Um, this presentation is on chromium-free refractories for copper industry. Although I'm going to speak a lot about copper industry, the refractory magnesia-chrome is used also in steel industry and stainless steel industry. So there will be some parallels for those who are interested. A big chunk of this work is in collaboration with Professor Ilona Jastrząska from AGH University in Poland. So let's get started with this. So copper manufacturing is pretty complex. A lot of us are very familiar with steel manufacturing from starting from iron ore. Big difference is that iron ore typically what is used in the industry is about 60% roughly has 60% iron content. Copper is a very different ball game. Your copper ore, which is mined either underground or open pit mines, they have about the world average is 0.5% copper, and Poland has about 1.7% copper. So you see, it's very low in copper content. So the challenge is very high to purify it to very high 99.99% purity. So let's get started. So first, after blasting and taking the ores out. They are crushed in big crushers. A lot of them are gyratory crushers. And then after that, it is ball milled into less than 100 micron particle size. And from there, this fine wet ball milled slurry is mixed with some chemicals so that the main the main copper ore, which is the CuFeS2, they float up, and this process is called froth flotation process. This froth is collected out and then it is dried to give you what is called as a copper concentrate. This copper concentrate contains 25 to 30% copper. It varies from country to country. So this copper concentrate powder is then charged into, here you see a flash furnace where you have the copper concentrate, some amount of quartz silica as a flux. And what exactly happens here is that your iron sulfide gets oxidized, about three-quarters of it gets oxidized and forms FeO. That FeO then reacts with this silica to form iron silicate or phylitic slag. So now you have a matte, which is the product from this, which contains 55 to 70% copper. And it is now much deficient in iron sulfide and more enriched in copper sulfide. So as a result of oxidation of this iron sulfide portion of it, you have a lot of sulfur dioxide as a byproduct, which is used later in the downstream process of electrolysis to make, this is converted to sulfuric acid, and that acts as one of the components that goes into the electrolyte. So there are several variants of this stage of the process called smelting, where you convert the ore into matte. This here you see an ISA smelt process, or which is one of the types of top submerged lands. That's what TSL stands for. So after this smelting process, you load this into a Pearsmith converter. This is one of, like, almost, I think, 80 to 90% of conversion happens in a Pearsmith converters, very common one. So ladles of matte are loaded into this, and then oxygen is blown into this. So what happens here is that your iron sulfide, it oxidizes to FeO, and which then reacts with flux and forms the phylitic slag. And then once the matte is oxidized to a level that the iron sulfide is very low, then the copper sulfide oxidation starts. So this is the second stage where you convert this copper sulfide to metallic copper. And then sometimes they skim out the slag, and and then blow again, and sometimes it's a continuous process. So what you get out of here is blister copper, which is about 98.5% purity. It's called blister because if you take this copper and solidify it, it will tend to have blisters in it. So, anyways, this 98.5% copper is still not done yet. It needs further processing. So, this blister copper is then charged into a refining furnace, an anode refining furnace, and there are a few variants of this. So, once it is put in this furnace, first it is oxidized to remove the remaining amount of sulfur. So again, it forms SO2, it goes out. Now, by this process, your sulfur is almost gone from your metal, but you end up having a lot of oxygen entrapped in your copper melt. So then this is then blown with natural gas, and this reduces this excess oxygen, and now you get 99.5% purity anode grade copper. This is generally cast into these anodes that are used later for electrolysis. So here you see the electrorefining process where this anode copper is converted to cathode copper, and now you have 99.9% pure copper that is sold in the market. And some people also put it in a vertical shaft furnace and melt it and process it through a continuous caster to make other sorts of products. So this in general is the copper manufacturing process. You see, it's a big journey from almost zero point 0.5 to 1% copper all the way to 99.9% copper. And the other thing is that the slag here is iron silicate, very acidic slag. That makes this process very challenging for refractories. You're looking at operation temperature somewhere from 1150 to 1350, depending on plant to plant and stages of the process. But this is a very harsh environment despite the lower temperature. So you can see the industry uses a variety of these furnaces. You going from shaft furnaces, isosmelt, smelter, copper decanter, Pearsmith converter, top blown rotary converter, electric slag cleaning furnace, and then a variety of anode refining furnaces from rotary to stationary to tilting. And in all of these furnaces, one thing is very common, and that is magnesia-chrome refractories is used for lining these. And there are a variety of these refractories from all the way from 15 to 17% chrome content to 32% chrome content, where it is called chrome mag refractories instead of magnesia-chrome. And a big challenge of these applications is that very high amount of slag in very acidic and very corrosive slag. So you see phyllatic slag contains about 45% iron oxide. This is a very common slag grade, and then 30% silica. And then if you do XRD of the solidified slag, you see that about half of it is phyllite, and then a big chunk of it, of the remaining one, is magnetite. So, and then there are some furnaces like Mitsubishi process and some other newer variants where they use a calcium ferrite slag. This slag is very corrosive, being very low viscosity slag. So, and then in Poland, due to the nature of the ore, they have a lot of lead content, and they have a different process also in one of the plants, direct to copper process, where they charge directly. Copper lead iron alloy into the converter, the Pearsmith converter, and you end up with a very corrosive lead rich lead copper iron silicate slag. And these slags are highly corrosive. So one of the weird mechanisms are thermal shock, because you go from batch to batch and you wait in between where your furnace cools down a bit, and a big majority of these furnaces are water cooled. So especially in the slag line, you end up cooling it pretty fast if you have a discontinuous supply of hot metal coming in. And then there is, of course, erosion due to charging of the materials into the furnace, and then there is tilting stresses, and then I've talked in length about the corrosivity of these slags. And one of the other things that is really corrosive about these furnaces, that in the upper portions of this furnace you have a lot of SO2 gas, and this gas is highly corrosive to refractories. It forms sulfates and causes volume expansion. So, very good. Chrome refractories are great. However, they during service, especially in contact with calcia and sometimes soda, soda is added in some of the copper furnaces to take out arsenic from the material. The arsenic vaporizes, so in presence of soda. So arsenic removal is helped by soda, but soda and calcia, these two guys, they convert a big chunk of the trivalent safe chrome variety to hexavalent chromium. And then this Cr6 plus is carcinogenic. It causes cancer. And people involved in, dismantling used refractories and then disposal of them, they are exposed to dust that is carcinogenic. They also cause skin and lung irritation. And these are very dangerous because they are easily water soluble, and if it is landfill then it slowly leaches into groundwater and causes long term water pollution. And you see that high temperature is not where this is active. It is the intermediate temperatures from 500 to 1300 degrees Celsius, especially in the 9 to 1100 degrees C, in the 700 degrees C. In this range it is very, very active. And you can see even with this 4%, this fluorescent yellow is the trademark of these hexavalent dangerous toxic chromium variety. And as you go higher up in chrome content, you end up with more and more. And this is only caused by calcia, unit calcia, or soda, and some of these alkali or alkaline earth metals to convert it to hexavalent chromium. And because of this problem, this issue, a lot of the countries are very strict. They restrict the hexavalent chrome content in the used refractories to less than 5 ppm, sometimes even less than 2 ppm. And this causes MAC chrome to be banned from several countries and several places, and that's where a lot of impetus has been to develop chrome-free refractories. So, before we develop a chrome-free refractory, we need to understand what makes macrome refractories so awesome. And after we understand that, then we will be able to develop better chrome-free refractories. So you see one of the most common variety, direct bonded magnesia-chrome on this slide. What you see in here is that the chromite and magnesia that are in this, the chrome forms a complex chrome spinel, MgFeCrAl Fe2O4, and this chrome, the bright regions, they get inside the periclase grains at high temperature during firing, and then during cooling they precipitate out as secondary chromite, this Sc. And this secondary chromite, this helps to bond the periclase with the chromite, the periclase with periclase, and periclase chromite with chromite. And all of this that generates a very high temperature resistant, a highly corrosion resistant bond, which makes these materials so highly performing. This is a more improved version of semi-rebonded magnesia-chrome. Here they use pre-fused magnesia-chrome aggregates as raw materials. You see these bright chrome-rich regions, and then you have the magnesia matrix. A blown-up portion is here. So these are secondary chromite precipitated inside the periclase or magnesia grains. And then you have some amount of monticelite, CaO, MgO, SiO2, or CMS phase. So because of this secondary chromite formation, you end up with a very highly bonded, high temperature resistant, high hot strength refractory product. So now let us look how does corrosion of this happens so that we are able to develop alternative refractories. So in this microstructure, you see the magnesia, it gets corroded on the outside. It forms magnesia woodstite or MgO-FeO solid solution due to the reaction with the phyllatic or Fe2SiO4 slag. The slag also leaches out magnesia, and phyllite is basically Fe2SiO4, right? And then the slag gets enriched in magnesium that is coming out of by leaching the refractory, and it forms more and more magnesia enriched olivine, which is a solid solution of phyllite and phosphorite. So, and then in the chromite grains, you see the periphery is getting reacted and forming magnetite, Fe3O4. So this is the slow dissolution process. And then you see a fused macrome grain. This microstructure is very typical of fused macrome grain. And you see that these fused macrome grains are slowly dissolving out into the slag and as Fe3O4 or magnetite spinel crystals. This is an inverse spinel. Now you see in this bottom portion the gas phase reaction, corrosion. So you see calcium sulfate. So this is the SO2 gas reacting with the calcium impurity present in the refractory, especially in the silicate phase, the monticelite phases, and that it converts it to calcium sulfate. This is a porous, high volume product, and the refractory slowly breaks out from those regions. Here you see it more clear. Oxychrome is a magnesia-chrome pre-synthesized aggregate, and you see this sulfate formation eventually forms a crack, and this high sulfate region is coming out of the refractory and spalls off. So now we are into this chrome-free refractories. Oh, sorry, I skipped a lot of slides. So one more post-mortem analysis. So this is a picture from flash furnace in Rio Tinto Kennecott in USA. You see that this is the hot phase of the refractory. A blown up image shows that a lot of copper sulfide from the mat has penetrated. You have copper arsenide intermetallics, and then lead bismuth precipitates. These are all like penetrating into the refractory and then mainly attacking the calcium silicate rich areas. You see a lot of highly corrosive phases like lead magnesium arsenide and magnesium arsenide. These are all helps to corrode away and dissolve away your grains. You can see the fused grains are getting destroyed and like getting washed away by the refractory, by the slag. Now here you see another example from a pure Smith converter. Here you see the hot phase, which has dissolved a lot of the refractories, and you see phases like delafoside, which is copper iron oxide due to the in the deep into the slag, and then you see olivine formation due to the leaching out of magnesia from the refractory and getting forming a solution inside the phylitic slag. So this is in general the corrosion process, and here you see this is a slower process than the later chrome-free refractories you will see in a bit. So one of the most common chrome-free refractories, especially used in the steel industry, is the alumina spinel bricks. You can see the alumina aggregates inside, and then you have a fine spinel matrix. So these are in this study reacted with an industrial copper slag. You can see the very high lead content, about 40% lead and 16% copper oxide. So highly corrosive slag, much more corrosive than what you see in the steel industry. And you see that something very concerning. You see the slag is dissolving directly your alumina grains. And what you have in the slag is this complex spinel magnetite forming a solid solution with the leached out alumina. And then you see that close to the refractory in the interface, you see this lead hexaluminate. This is like your CA6 phase, very well known in the castable world, refractory castable world. This is an analog of that lead hexaluminate, and this is directly dissolving out your these large alumina grains. Possibly like white fused alumina. So this is very bad because you don't want direct dissolution of your refractory aggregates like this. If your aggregate is dissolving like this, your matrix is going to be like washed away pretty easily. So, and this same phenomena was found in another study. They did a lab induction furnace rotating finger test. You have like bars of refractories dipped in steel and rotating in, dipped in copper, sorry, and rotating in copper slag. And you have the metal line and then you have the slag line. And obviously we'll have more corrosion in the slag line. And they studied a variety of refractories from magnesia-chrome, the traditional one, versus magnesium, zircon, and then alumina spinel. And you see that this is after, I think, 24 hours, you see very little corrosion. And then this is alumina spinel before and after corrosion. And after corrosion, you see even after 2 hours, it was completely gone. It was completely washed away. This is magnesia zircon. And again, this only lasted 6 hours. This was getting highly corroded. So you can see none of these are even close to the performance of magnesia-chrome. So the takeaway from this is that alumina, zirconia, silica seem to be really bad for copper application for this kind of acidic slags. A microstructure of this shows you a little bit of the corrosion process. As I said, like, the olivine phase gets enriched in phosphoride, which is coming from the dissolution of magnesia. And then this is, you can see the slow dissolution of the magnesia spinel. And then this is, you see more prominent dissolution of the arsenide solid solution. So magnesia, arsenide spinel solid solution. So out of these, you see that magnesia spinel has better prospect. That's the takeaway. So now, after all this literature survey, what we realized is that there are many different organizations, industrial labs and universities and national labs that are doing this post-mortem analysis, sometimes from lab tests and sometimes from actual field trials. And there is no, like, they are not in the same level of comparison. They cannot be compared directly. So one of the challenges that, okay, they are showing newer and newer corrosion mechanisms, but in order to develop a chrome-free material, we need to have a same way of analyzing these materials. So that's when I started working after my PhD. I started as a side project, outside of my work, working with AGH University with Professor Ilona Yatroska and her master's and PhD students. So over the years, I have been fortunate to mentor a few of her students, Thomas, you can see Olivia, Veronica, and sometimes I write papers with Joanna. So and along these years, we uncovered a lot of good insights into development of chrome-free materials, and the goal is to identify which phases, which compounds are better. So and this is what you will see being summarized in the following slides. So one of the first things we did is that what was done by them is that thermodynamic calculations using the FactSet software. And we used macro refractories, and with that, a 70-30 mixture of magnesia with 30% of each of these spinels, Mgl2O4, arsenite, magnesium titanate or kandilite, the zinc aluminate or garnite, and then magnesium orthostanate. So these spinels were compared, and from there we got insights that few of these phases are promising, and this is theoretical analysis, right? We need experimental validation. We are the beauty of this software is that you can also predict viscosity from this, and from there we realize that if we are able to have a spinel with zinc aluminate and small amount of iron at solid solution, then you get a very high viscosity slag that is always beneficial for improving corrosion resistance. So from these insights, from these theoretical insights, we a series of experiments were started. So one of the nice techniques to pre-screen potential phases is your hot stage microscopy. What you do here is that you have a fixed slag composition, you make a cube out of it, you have refractory substrates, and then you heat it and you observe the evolution. And what you observe is the height change of the slag, and then you observe the contact angle at the interface between the slag and refractory. And this gives you a very nice estimate of what's going on. And from there, we studied a lot of these substrates versus the same slag. And you can see that the magnesium titanate and zirconia, the slag melts very fast. That means that these are not corrosion resistant. On the other hand, you see macrome and magnesia. Macrome starts a lot later, and then magnesia always starts early. It continues to a higher temperature. This is the contact angle at the interface, and you can see that again, macrome, the contact angle evolution, the reduction in contact angle happens at a lot later temperature. The onset temperature is a lot higher, which means that macrome is very good, and we also know that from practice. So if I try to summarize this in terms of tables, these 100% height temperatures, this is like the onset of the shortening of the slag pellet. You see that the temperature is very low, only 1409 for alumina versus macrome is 1424 and magnesia is 1414. So clearly magnesia, the refractory should be a basic brick, not a alumina based brick. That this is the takeaway from this. Now from the candidate phases, you see that these magnesium titanate and zirconia, they have very low temperature versus magnesium aluminate and zinc aluminate. So because of this, these are primary candidates as potential candidates, and you can see a macrome as a standard as a point of reference. However, upon observing magnesium standard and zinc aluminate, which seem to be very close to each other. In fact, magnesium standard looked apparently better, but from a post-test image, you can see that the slag has spread out pretty fast in magnesium standard, which sort of aligns with the initial fact-stage thermodynamic calculations that were done. So for sure, magnesium standard is not a candidate, and zinc aluminate is a potential second phase to be used in your magnesia spinel bricks. So this gives you direction of what to use. Now we also did cross section of these materials. So basically we took a portion from this and did a SEM analysis. So this is what you see in here. The slag, which is phyolitic slag, this composition, you see a lot of Fe3O4 and Fe3O4, Mg2O4 solid solution in the slag, these grains, and then you have a lot of glass. And then you see the direct dissolution of your alumina into the slag, and sometimes it forms these Al2O3, Fe2O3 solid solution in the interface. The zirconia, again, it gets dissolved and forms zircon in reaction with the phyolitic iron silicate slag, and this is not good. You don't want direct dissolution of your refractory, and then due to this, sometimes silica is precipitated. Magnesium titanate, if you zoom up, zoom in into the slag, you see a lot of these phases. You see U phase, which is alvospinel, solid solution with magnesium ferrite and iron titanate. And you ask yourself, where is this titania coming from? Where is this magnesia coming from? It's coming from the substrate. And this is bad news because your substrate is getting heavily dissolved and reacted into the refractory. Also, you see that you have formed iron titanate and magnesium titanate solid solution, this I phase, elongated ones. Again, your magnesia and titania are getting dissolved again, dissolved into the slag. You're forming phosphorite. This is all bad news. You don't want any of these into the slag. And deep into the interface, you see also reaction, but it has slowed down because here the slag is saturated with magnesia, and then deep into the refractory, you see the pristine unreacted magnesium titanate and then MgTiO3, which is a common impurity in Mg2TiO4 based refractories. Magnesium stannate, you see a similar thing, a lot of reaction and formation of these released tin oxide, these white spots, and a lot of olivine rich in phosphorite, and that is bad news because your magnesia is getting dissolved away. However, with the standards, you see that there is almost like a reaction layer formed, which is magnesia woostite solid solution, this W phase, and then you have some amount of little bit of phosphorite close to the refractory interface, but not enough in the slag away from the refractory. So this is an indication that when you're checking the slag away from the refractory and it does not have any new phase, just the phases that are normally present in pure slag, then you know that, okay, it's good news. You have very little corrosion of your refractory. And then you see macrome, very little reaction of the refractory, and this is all, and you know that these are standard products used in the industry. Now you see the candidate magnesium aluminate bonding phase as a having very low reactivity, and there is a little bit of solid solution formation which is beneficial to form a passivation layer. And then this is due to the magnetite going into solid solution with your spinel phase. And similar observation you see in zinc aluminate, just that there's a little bit of difference in the layer formation, the protective layer formation. So, as I said earlier, zinc and iron doping into magnesium aluminate spinel is showing benefit, and it tends to give you a higher slag viscosity, which is beneficial. Not only that, when you look at the interface, the other than this, the phases are the same, exact same, but at the interface you see a little bit thicker protective layer, and this layer formation is beneficial in terms of slag corrosion. So the takeaway message is that zinc and iron doped, you want more zinc and less iron, because iron, you don't want a lot of it, it will form liquid phase. So 3:1 is a good ratio, and then 23% of this mixture was added. One of the other benefits other than the protective layer formation is that zinc and iron doping 3:1 gives you better sintering of the matrix, and you get to densify your matrix better, and a denser, smaller pore size matrix is always beneficial for corrosion resistance. Here you see pressed pellet dilatometry. Without spinel doping, you see the shrinkage at 1500 is only 0.8%. With more and more doping, the shrinkage is increasing, meaning you are getting better and better sintering. And then the sintering expansion is also less with more doping, which is always beneficial to have a low porosity, high density material. Not only that, your abrasion resistance also increases. So if you have a basic matrix, magnesia rich matrix with zinc and iron doping, your abrasion resistance is increasing and your hardness is increasing. You don't get to the level of alumina, zirconia, the wear resistant ceramics, but you are improving from the starting point of magnesia, and that is beneficial because you have a more wear resistant, erosion resistant matrix. If you do look a little closer, what you see that after this abrasion tests with silicon carbide grit, you see that in magnesia, you have big scraped patches of like missing material and this uniform abrasion of the material. Whereas in the zinc and iron doped, you see a lot of this spinel precipitates, and it gives you some sort of precipitation hardening effect. And these precipitates help to improve the abrasion resistance. You don't have these smooth patches, you have more of grooves and micro cracks. These are like, just giving you indication that it is really resisting the passage of silicon carbide grit particles on its surface. So this gives rise to the abrasion resistance. Now, the one of the challenges with magnesia spinel materials is that it debonds and you don't get very good bonding. If you look at EDS analysis, you see that there is very little interdiffusion of magnesia from either side. So this prevents you from having a good bonding. Whereas if you have a zinc aluminate matrix, you see that a large amount of zinc penetrates into the magnesia side, deep into the magnesia side, and this gives you a better chance of forming bonding phase. And this interdiffusion further enhances if you have spinel, magnesium aluminate spinel in the matrix. And as I was saying earlier, the debonding happens due to the large thermal expansion coefficient difference between the magnesia aggregates and your zinc aluminate and spinel phases. And you get to counteract a little bit of that due to the high zinc interdiffusion into your magnesia aggregates. So you are better off that. But just be mindful that don't add zinc aluminate like blindly. People who have tried to have a lot of in situ zinc aluminate end up having a lot of Kirkendall porosity, which is basically the diffusion rate of zinc is very high compared to alumina, and you end up lots of vacancies, pores in the zinc side. And you see the zinc diffuses into the aggregate, alumina aggregate, but then it leaves behind pores. So you have to optimize, and the best is to use a preformed spinel. If you use too much of this in situ zinc aluminate, you end up with a lot of porosity, higher porosity than magnesium aluminate, and then lower hot strength, which is never good for a refractory. So if I conclude all these learnings, what would future chrome-free refractory look like? It will have a lot of these magnesia aggregates fused, preferably fused magnesia 50%, 3 to zero point 0.1 millimeter of different particle sizes to give good packing, and then some amount of aluminum spinel, which is easily available in the market, mostly in the medium and fine ratios. The higher surface area gives you better corrosion resistance. Now, as we know, zinc aluminate has better diffusion into magnesia, so zinc aluminate should be used, and then it gives you corrosion resistance, and zinc and iron doping helps. So your matrix, which is the remaining 36%, what would that be? Preferably 18% preformed spinel and 18% preformed zinc aluminate, and I have published a paper on this. There's a very easy way to manufacture it at 1050 degrees Celsius. You can make preformed zinc aluminate powder that can be used directly in the refractory. An alternative and cheaper way would be to add 1:1:2 actually, to form 1:1 in situ spinel of zinc aluminate and magnesium aluminate in the matrix. And then another idea would be to have 16% magnesium aluminate, and you have 20% doping of this 3:1 zinc and iron oxide. And then a variant of this can be, you can have in situ spinel. The in situ spinel are given as suggestions because you have to optimize the pore formation that generally forms as a result of it. So all of these four are candidate phases, and this would be something for ongoing research to develop into a really corrosion resistant chrome-free product for the market. And with that, before ending, I would like to briefly mention that there is an ongoing call for papers going on in the International Journal of Ceramic Engineering and Science in the American Ceramic Society. This is on environmentally responsible refractories. Myself and Professor Yatroska are guest editors there, and this is about you can, if you're working on, hydrogen-based iron making or steel making, or new ways of manufacturing of steel, then this would be very good for this special issue. A lot of environment-friendly refractories like chrome-free refractories for copper, steel, or cement, and even like green manufacturing process, like anything to do with reducing firing temperature, reducing dry out times, improving energy efficiency in steel and glass industry. All of these are candidate papers for this. And then if you're working on low cost aggregates using like local raw materials as alternatives of high fired or even fused aggregates, those would be also candidates for this call for papers. So I encourage you all to submit papers. There are multiple ways to counteract article processing charge. If you're working with a university, a lot of the universities have waivers for them. So please reach out to me if you are interested in this. So with that, I open the floor for questions.
Okay, Dr. Mandal, it was a very nice talk. So,
Thank you very much.
yeah, I think we have a lot of audience. So, may I ask request to audience? If you have any questions, you may ask now. The
Yes,
floor
please.
is
I see raised hand from Ankita Das. Please
Ankita.
ask.
Can you can ask question directly?
Yes, sir. You mentioned that the debonding is better with zinc aluminate spinel. So can you please explain that? Like
Yeah,
the debonding.
yeah. So debonding happens in both the refractories due to the expansion coefficient of zinc aluminate and magnesium aluminate are almost same versus magnesia aggregates. So the debonding happens in both. However, when you have magnesia, there is no chemical interdiffusion across the interface. So you have debonding due to TEC difference, but no chemical diffusion. In zinc aluminate, you have debonding, but you have interdiffusion or deep diffusion of zinc from the zinc aluminate side into the magnesia side. So this gives you a better advantage of being able to form a better bonding in your break. But how do you counteract this debonding? Because your TEC is not changing due to chemical diffusion. You do that by in the matrix, instead of having, let's say, you look at only the matrix. So 36% of your composition is your matrix. I'm just giving you an example. So from that, instead of having 36% pure zinc aluminate, maybe have 50-50 magnesia and zinc aluminate. So now your expansion coefficient, instead of being here, you are somewhere here. And due to the difference, reduced difference between TEC, between your new matrix versus the aggregate, you will close up your debonding and you will have a better bonded structure. You don't want zero debonding, because this debonding actually is helpful for good thermal shock resistance. So you need to strike a balance. And that's why a lot of refractory scientists are hired in the industry, because they need people who understand these nuances and develop better products that replace the existing competing product in the market.
Okay, sir. Thank you.
You're welcome. Please ask questions
Any
like.
other questions from the audience? I think many students are there probably.
For all the students, like, please ask questions. This is like a very good learning opportunity for you. And there are
Yeah,
no,
Dr.
like,
Madan, in terms
yes.
of corrosion resistance, which one is more beneficial as compared to chrome, like magnesium aluminate or zinc aluminate?
In terms of corrosion resistance for copper slag, they are both very similar. You will have to use both of them. Probably like you have to work on the ratio. Maybe 1:1 is a good starting point in the matrix.
Okay. In terms of temperature resistance,
In terms of hot strength, you will have, if you compare a pure magnesium aluminate matrix versus a magnesium aluminate zinc aluminate matrix, 1:1, you will have better hot strength in the zinc aluminate magnesium aluminate combined matrix, because there is very high diffusion and solid solution between zinc aluminate and magnesium aluminate.
is there any publication in this topic, like both are mixed together and we do some better product?
There are a number of publications. I myself have several publications on this. So this is a very active field. So feel free to write me a message separately and I will send you some papers.
Yeah, yeah, sure. Thank you.
Hi, Somnath. This is Shantanu from TRL Closing. I have one question. This industrial application of this zinc aluminate and magnesium aluminate, is it in the industrial uses has been happened, or it is still in the lab scale?
I know some companies, and I cannot name them. They have already trialed basic bricks, meaning magnesia-based bricks with zinc aluminate and zinc aluminate magnesium aluminate matrix, and apparently good results were received. There are not enough publications of postmortem analysis, so that makes it difficult to openly talk about it.
Okay, thanks.
This, so far, what I have seen, this is highly promising. There is very good potential of this sort of material for both steel and copper application. In copper, there has not been any field trials that I know for sure.
Hello.
Hello.
Yeah. First of all, thank you for a very nice presentation. I think you clearly, demonstrated how zinc aluminate and along with the magnesium aluminate can give a very good chrome-free refractories. I just wanted to know about that. You mentioned about the corrosion studies. No? You mentioned that wear as well as infiltration. You study and you compare. So generally, how would you differentiate these two when when you test in the lab? I'm not talking about microstructural study. Can you test in the lab and differentiate what is due to wear and how it is infiltration taking place? I mean, just want to know how exactly that, because infiltration is mainly due to the amount of porosity and pore size, another thing like that, right? So how do you generally differentiate in the lab?
Um, Induction furnace tests where you have bars of refractories dipped in your melt, which has copper matte and copper matte on the bottom or pure copper on the bottom, and you have slag on top. These are
Okay.
commonly done in the industry.
Okay.
Currently, this magnesia aggregate based refractory with zinc aluminate or zinc aluminate with spinel matrix, this is currently ongoing. So this has not been done yet. But this is the way to do it. So for sure, this will be done. It's a matter of
Okay.
who does it fast.
I just wanted to ask you whether this type of refractories can be used for high temperature, other foundry application other than copper, say temperature up to 1600 degrees Celsius or so, or is it good for only for the copper industries, or you said about 1300, 1350 or so? Is it like that, or is it fit for that use, high temperature
Magnesia,
use?
yeah, magnesia bricks. So magnesia zinc aluminate or magnesia spinel zinc aluminate. So basically magnesia aggregates. And let me show you. A concept like this where you have magnesia aggregates and some spinel aggregates, and you have a matrix of magnesium aluminate and zinc aluminate with some amount of fine magnesia. This is also a candidate refractory for RHD gas or snorkel. So this is 1600 degrees Celsius steel making application directly in competition with macrome bricks. So some works have already been done. As far as I know, that these have already been trialed. So these are for sure good candidates. You don't want iron doping in for steel making applications. This is specifically for copper application.
The slag resistance will be good at high temperature, at those
Yeah,
temperatures.
yeah. I have seen that there are papers from Brazil who have tested refractories based on zinc aluminate, and they have found better corrosion resistance versus just magnesia spinel or alumina spinel. So generally, zinc aluminate, you only want partial substitution. It works the best, and that gives better corrosion resistance.
Okay, thank you. So any other questions from the audience? Please go ahead. I think
Am
if
I
there are
audible,
no
sir?
other questions, yeah, please go ahead. Please go ahead.
Sir, I am Dipanjan from IIT BHU. So, sir,
Hello.
I have two questions. Hello,
Yeah.
sir. Am I audible?
Yes. Yes. Go ahead. Ask your questions.
Sir, I have two questions. One is, how did you perform that viscosity test of different compositions? And sir, one more question is that as that copper slag, copper furnace slag is basically as acidic slag. So when you use that magnesia aggregate, which is basic in nature, if it affects that aggregate.
Yeah, so very good questions. In the viscosity plot that I showed you right here, this is from FactSage thermodynamic calculations. So it gives you predictive values of a desired refractory with slag mixture. Let me break it down a little bit for you. So what you see here is that this is magnesium stannate 30% with 70% magnesia. So that's your refractory. Now this refractory is mixed 50% with slag. So you have 50% refractory, 50% slag. So whatever composition you get, this you put in the FactSet software, and you put temperature 1400, 1350, so on, and at each temperature it gives you the composition, how much liquid you are forming, how much solid solution you are forming. So from that liquid you get the liquid phase percentage. This is this plot, and it also gives you viscosity values, and from there you plot the viscosities, and then you can compare one refractory versus the other. So this is the theoretical simulation or prediction of viscosity. This is not real viscosity. If you want to do real viscosity, what you need to do is that you grind a 50-50 mixture of this slag and refractory, and then you put it in a high temperature platinum viscometer where you have a spindle and you have a crucible, and then you heat it and you rotate your spindle, and from the torque measurement, just like a room temperature viscometer, you measure the viscosity at high temperature of slags. And this is also done by some research groups. This is very expensive method to do viscosity, so there are very few papers in general. And also you need to worry about your platinum reacting with your slag, because some of them also contain like some elements that are not compatible with platinum. So there is a little bit of challenge here. So that's how you can get the viscosity measurements from your material. Sorry, I forgot the second question. What was the second question again?
So that was that if that said as that slag is acidic in nature, so then
Aha.
if we use that magnesium aggregate, so there is a problem.
Yes. So yes, so one thing is theory, right? That from theory, you know that magnesia is basic, the slag is acidic, so it should react, whereas alumina is amphoteric or neutral, so it should react less. But in reality, that's just a preliminary indication. But in reality, what happens is that your alumina gets washed away by the slag due to formation of new phases. In this case, you see lead alumina based compounds, right? Lead hexaluminate. So because of these compound formations, and even with phyletic slag, the reactions happen. And because of that, you end up losing your alumina a lot faster than your magnesia based materials. This is like after 2 hours, it got washed away. This is after 6 hours, and I think this is after 24 hours. So this just tells you that the basic bricks are a lot more compatible, just because your basic brick tends to sort of forms a little bit of passivation layer with your slag, because it forms magnetite at the interface, and then magnesia woostite solid solution, and then little bit of also olivine, which is enriched in phosphorite, and that kind of like forms a dead layer, or sort of like a passivation layer at the interface. So here you see like magnesia woostite layer formation, and this happens in reality also, and this gives you end up giving you a better corrosion resistance. So again, this you have a basic slag, use a basic brick. You have acidic slag, use acidic brick. These are very early surface level guidances. But when you are going into like specific slag, specific temperature, specific refractory compositions, you have to observe what reaction phases are forming, and you have to actually run tests like induction furnace tests with fingers of your refractory rotating in the slag to get a better idea. And then you have to cross section it and figure out how much of these phases are forming. And let me tell you this, these sorts of microstructural analysis after corrosion test and after field trials are very common in the industry. People actually cut sections and polish them and deeply study what phases are forming. This is how a lot of the global refractory companies are operating. So these are not purely academic things. These are like very industrial, real world, like real process of filtering out which refractory works better, which is not that good.
Thank you, sir. Sir, I have one more question.
Yeah.
Sir, that if we use that zinc aluminate matrix with that magnesia aggregate, so there is some diffusion between this. So in that process, that magnesium aluminate can form, and there is some expansion happen. So how it counter this expansion?
There is no expansion that happens when you have diffusion of zinc from zinc aluminate side into magnesia side. Actually, when you have a magnesia aggregate, let me show you this picture to become more clear. So when you have zinc diffusion from your zinc aluminate side into your magnesia side, you form ZnO solid solution, not MgL2O4 on this side. And then you have a little bit of magnesia going into the zinc aluminate side. Here you have zinc aluminate magnesia solid solution. So basically Zn, MgAl2O4. So it's not fresh in situ magnesium aluminate solution as in the reaction of magnesia and alumina. There is no free alumina in here. So because there is no free alumina in this system, there is no free in situ spinel formation. All there is happening is ion diffusion across the interfaces, and so there is no volume expansion, like nowhere as close to what happens in an in situ formation. For sure there would be lattice constant difference between spinel pure zinc aluminate versus magnesia solid solution zinc aluminate, but that is nowhere close to what volume expansion you normally get when you have in situ magnesium aluminate formation. Even in situ zinc aluminate formation, you have volume expansion due to Kirkendall effect, due to pore formation. So none of that happens in these diffusion studies. So pore formation is not a problem in this scenario.
Okay, sir. Thank you so much, sir. Thank you so much.
You're welcome. Any more questions? Just feel free to ask. I like answering questions.
Yes, I have one question.
Yes.
As earlier discussion, you had told me that this can be used for RH snorkel bricks. Okay.
Yes.
Then what is the impact on thermal shock resistance? Since it does not contain secondary chromite based spinel, then how we can improve this thermal shock resistance of this RH snorkel bricks, means chromium free.
Yeah. So in your macrome brick, you have a lot of magnesia aggregates, and then you have chromite and macrome co-fused or co-sintered grains. So your magnesia aggregate will have, let me show you this curve. The reason why you have high thermal shock resistance of macrome brick is because you have high expansion magnesia fused or sintered, and then you have macrome fused aggregates, and if you have MgCr24, it will be somewhere around here. So due to this delta in the thermal expansion coefficient, you have little bit of debonding and microcracking that gives you thermal shock resistance. Okay, so that sort of difference is already there in your zinc aluminate. So you have the benefit of the debonding due to TEC difference. What is missing is that you don't have the solid solution formation
Yes,
that gives you
yes.
the hot strength. That you can get it from the zinc aluminate addition and combining it with magnesium aluminate.
And it is applicable for means iron oxide rich slag.
Yes,
Since
yes.
how
It
it is
will it
means what
It will
what
still
is the
be a basic, it will still be a basic brick, meaning a big chunk of your brick, probably more than 60% of your brick will be magnesia. So a lot of the corrosion resistance comes from the magnesia aggregates, fused magnesia preferably. And then your matrix, the function of the matrix is to bond and form a relatively corrosion resistant matrix material. And this will come from your zinc aluminate, because if you want to replace chrome, what else do you use? Your bonding phase is chrome iron aluminate solid solution, right? MgFeCrAl Fe2O4. If you want to replace that, there is hardly anything that you have up in the market other than magnesium aluminate and zinc aluminate. These are your only two options. So if you want to make a really chrome-free product, you sell chrome-free product not where you are trying to get low cost material. You sell chrome free product where chrome is banned. You have no option. That's where you do it. So You see the difference. You see cement plants in Japan. They use magnesia spinel bricks in rotary kiln in Japan. Okay, because chrome is banned because the cement has high calcium that forms hexavalent chromium due to reaction with your chrome bricks. However, in India and a lot of countries, we have chrome bricks in cement plant. Why is the case? Because there is nobody who is banning it. So as long as you have the allowance, the permission, you will use chrome brick because it is always low cost and it is really good. There is nothing that beats the performance of chromium containing refractories. But the presence of hexavalent chromium, the environment aspect, that stops you from using it. And now it's a company's decision. Do you want to make chrome-free material or not? You see, it's a very different decision-making point.
Yes, clear. How much percentage are you doping this thing? Means zirconia.
So here you can see that this is just a concept. You can have about 50% magnesia and then 14% your grains of spinel, and then in the matrix you can have a variety of preformed and in situ forming spinel. You can vary it to get a balance of bonding and porosity.
Okay. Thank
Try
you.
it out. Yeah.
Yeah. Thank you.
Any other questions from audience? If not, let us thank today's speaker, Dr. Somnath Mandal, for this very interesting and very informative talk. In fact, I invited him for about 10 days back and immediately agreed despite his very busy schedule and travel plans. So thank you so much. And joining very early morning, and giving this presentation. Thank you so much. And I would like to thank all the members, participants, mainly from industries and students and academia, who really, made it more interactive. Thank